Let's take what we know about the quotient-remainder theorem and do some true-false questions. Now, if you get a true answer, I want you to prove it using a direct proof, and that gives us good review. If you get an answer that's false, I want you to give me a counterexample to negate the original statement. So our first practice problem. If 6 does not divide n, then cosine of n pi equals -1. Okay. You can use any integer you want to for n. Remember, what you're dividing into can be 0, positive, or negative. I think a lot of people would do better if you think about n being positive. So why don't we say 6 doesn't go into 7, so if n is 7 in this case, would cosine of 7 pi equal to -1? Yes, it does. Okay, so let's try 8. 6 does not divide into 8. In this case, n is 8. So cosine of n pi would be cosine of 8 pi. But wait a minute, 8 pi is coterminal to 0. So cosine of 8 pi actually equals 1. Now I know the statement is false. So if we write it up a little more formally, we're saying the statement is false, so we need a counterexample. So I want you to consider that n is 8. Now, remember, if you want to negate an if-then statement, you choose an n value that satisfies the hypothesis but denies the conclusion. So I need to look at the conclusion. So what is cosine of n pi? Well, in this case, it would be cosine of 8 pi. That's equal to 1, not -1. So to negate the original statement, 8 supports the hypothesis but makes the conclusion false. And there's our negation. Moving on. For all integers k, if -1 to the k power equals -1, then 4 divides k squared plus 3. This one's a little more difficult, so how about we do some scratch work? So in playing around with the hypothesis, I know that -1 to the first is -1, -1 squared is +1, -1 to the third is -1, -1 to the fourth is +1, and these powers are just going to keep alternating. So I notice that -1 to the first, third, fifth, and for that matter, any odd exponent is going to be -1. So the hypothesis tells me that k is odd. Now, if k is odd, I know the definition is that k is equal to 2n plus 1 for some integer n. So let's look at k squared plus 3. Well, that would have to be 2n plus 1 squared plus 3. Well, I know if I square the binomial quickly, I get 4n squared plus 4n plus 1 plus 3. Well, that's 4n squared plus 4n plus 4. So I see that, in fact, 4 does divide this expression because I could factor out the 4 and make it n squared plus n plus 1. And what I know is that n squared plus n plus 1 is an integer. Now that we know that this statement is true, let's review how you go about writing a direct proof. So remember, you suppose that the hypothesis is true. So I'm supposing that k is an integer such that -1 to the k equals -1. Remember, -1 to the k equals -1 told us that k is odd. And since k is odd, we know the definition is that k equals 2n plus 1 for some integer n. We then plugged 2n plus 1 in place of the k in the k squared plus 3. And when we worked it out, we realized that 4 actually was a factor of the big quadratic expression here. Therefore, 4 does divide k squared plus 3. So let's try one more true-false statement. Whoa, we're going to review method of exhaustion. So if 2 divides n, but 4 does not divide n, and n is between 0 and 20, then I to the k equals -1. Let's check it out. So in this case, 2 divides n. That means n's a multiple of 2. So I've listed all the possibilities that are multiples of 2 that range anywhere from 0 to 20. But 4 does not divide into n. Well, 4 doesn't divide into 2, so leave it in the list. 4 divides into 4, so omit it from the list. In fact, 4 divides into 4, 8, 12, 16, and 20. So what that does is it only leaves us 1, 2, 3, 4, 5 possibilities. And the method of exhaustion tells us to test each possibility. So I'm going to say, well, what is I squared? What is I to the 6th? What's I to the 10th? What is I to the 14th? And what is I to the 18th? Well, we have memorized that I squared is -1. I to the 6th, remember, we can break into I to the 4th times I squared. This is going to be 1 times -1 equals -1. Well, I to the 10th, we can break down similarly. You can make it I to the 8th times I squared. So you can always use powers of 4 because we know that I to any power of 4, where the power is a multiple of 4 is 1. So we get 1 times -1 again. This is I to the 12th times I squared. So once again, 1 times -1 is -1. And I to the 18th is I to the 16th times I squared. So I have proved by the method of exhaustion, I tested every option available to me. I have proved that the original statement is true. Here you'll see that I've written this up a little more neatly and more compactly to where I'm just telling you that every option does equal -1. We figured that out with our scratch work. And now we're going to go from method of exhaustion to a new style of proof that's very similar.